In this intro video, we will be talking about projectile motion, which I always thought was kind of a fun topic in physics because it involves launching things through the air. And it's kind of fun to be able to predict how far things are going to be able to go and where they'll be able to land and everything else like that. Understanding projectile motion involves you being able to understand the idea that when you have motion that's in perpendicular directions, the motion in each direction is independent of each other. And you should already know this from dealing with vectors. It's something that happens in the horizontal direction cannot affect things that happen in the vertical direction. That being said, this is still a very difficult concept for people oftentimes. If we look at a dropped ball and a thrown ball, as illustrated in this picture here, if I drop a ball, it of course accelerates downward. So you see the distance the orange ball moves is greater in each moment of time. So each image of the ball is taken at an equal spacing apart. So let's say like every second. So in the first second it moves this distance, in the second second it moves even farther. And that of course is due to the acceleration of gravity. If you take a second ball and you throw it outwards horizontally with no vertical component, that ball will match in time the exact same height. And so they will hit the ground at the exact same moment. This is often, again, it's a hard thing for people to understand that this does in fact happen. So there's an example from Mythbusters where they took a bullet and they fired a bullet here on this video downrange, and at the same time they dropped a bullet from this rig, and let's watch what happens. So you can see on the high-speed footage here, the highlighted bullet comes and hits the ground, and the shot bullet comes just a moment later. Again, they had already figured that there was about a 3 millisecond difference in when the gun fired and when the bullet actually dropped. So the difference we're seeing here is actually the difference they expected based on the timing of their rig. So you can see with something even as moving fast as a bullet, if you fire it perfectly horizontally and you drop something from the same height at the same time, they are both influenced by gravity equally, and they both hit the ground at the same time. Kind of a slightly different example of the same theme is this whole idea of this monkey and being shot by a gun. So let's watch the setup here. It doesn't seem to want to play. So the golf ball gun is angled so that it is pointed exactly at where the monkey is. So if there was no gravity, the bullet would come out and it would head straight for the stuffed monkey. But however, it is gravity. So at the moment the gun is fired, the monkey will be released from the catch, and it will fall. The bullet will also fall. Its trajectory will curve. And so we'll watch what happens. And in slow motion, towards the monkey's original position, but as it curves due to gravity, the monkey is also falling until it hit perfectly on. All right, let's go back to the presentation here. So we need to figure out what equations of motion do we use in the x and y or in the horizontal and vertical directions when we're dealing with these types of problems. The first question we have to ask ourselves is what type of motion is there in each direction? In the horizontal direction, we have constant velocity because there is no force in the horizontal direction. The equation of motion for a constant velocity is just distance equals speed times time. When we're dealing with projectiles, we just put distance in terms of x, so we know that we're dealing with the horizontal component, and then we talk about vx because that is the velocity in that horizontal direction, and then time. In the vertical direction, we have constant acceleration. The acceleration comes from the force of gravity. This gives us the equation of motion we've always used is y equals vyt plus 1/2 at squared. Or if you use the value of g for acceleration, y equals vyt minus 1/2 gt squared. Just putting a positive 9.8 in for g, but it is negative overall, so that's where that minus sign comes from. Projectiles always take the same path, which can be modeled as a parabola. If you look in the grand scheme of things, it's actually part of an ellipse, but we're not going to get into that right now. But as a parabola, and what happens is you can see the blue arrow represents the horizontal component of the speed, and you can see the entire time that doesn't change. The red represents the vertical component, and you can see that first gravity slows it down until it stops, and then as it falls back down, it speeds it back up the other direction. A couple things to notice about the parabolic path is the maximum height is always when you're halfway through the flight, so time is equal to half the overall flight time. And your takeoff and landing speed are equal. The velocities are equal and opposite, but since speed doesn't have a direction, they're equal. So whatever speed you take off at, that's what speed you land at. Also, whatever angle you take off at, that's the angle you land at. That is both of these things, the maximum height and the takeoff and landing, assume that you're taking off and landing at the same height, so that your overall vertical displacement is 0. The other thing to know about projectile paths is that if you fire projectiles with the same velocity, if they have complementary angles, so 70 degrees and 20 degrees, they will have the exact same range. The greatest range comes from a 45-degree angle shot. That takes the best advantage of both being in the air for a long time and also traveling fast downfield. In physics, we want to look at there's 3 different types of problems that can cover a lot of the different types of problems that will come up as you are doing projectile motion. So when you're doing a question, you can just ask yourself, what type of problem is this? And then look back on examples of how you went through it. So they're either the Thelma and Louise problem, the Dukes of Hazzard problem, or the combined Thelma and Louise and Dukes of Hazzard problem. In a Thelma and Louise problem, at the end of the movie Thelma and Louise, they just drive off a cliff. They decide to end it all. So the Thelma and Louise problem is the type of problem where the projectile has a velocity that's only in the horizontal. So this car is only driving horizontally at a velocity of 35 meters per second. It also starts up above something. So there's a height, it's on a cliff that has a height of 100 meters, and we want to find the range. Here again are our horizontal and vertical equations of motion. If I plug in the numbers I know, x I don't know, that's the range. It's equal to Vx, 35 meters per second, times the time it's going to be in the air, which I don't know either x or time, so I cannot solve this first equation yet. For the y equation, y is negative 100 meters. I should have put the unit on there, I apologize. It's negative because it's moving down, so I'm choosing the down direction as negative. That equals negative 4.9 t squared, because Vy I really should have left in there as 0, because this is only moving horizontally. There's no vertical component to the velocity. Solving this second equation then for t gives me a t of 4.5 seconds. And then if I put 4.5 seconds into the first equation, that gives me a range of approximately 160 meters. In the Dukes of Hazzard problem, because in Dukes of Hazzard they never drove off cliffs, they drove off jumps. So because the car is going off a jump, its velocity of 35 meters per second has both a vertical and a horizontal component, a Vx and a Vy to it, and we need to find those. We can find those just like we found forces and force vectors. When we plug in the numbers 35 meters per second and 30 degrees into these equations, we get the x component is 30.3 meters per second and the y component is 17.5 meters per second. Now, we're assuming that, even though it's not maybe drawn the best in the picture, the General Lee is going to take off and land at the same height. So that gives us an overall displacement height of 0 meters, since this height that it starts at and the height that it lands at are the same. Plugging in what I know, x is now equal to 30.3 times t. Again, I can't solve this for the range yet because I don't know x or t. For the y equation, we get that 0 equals 17.5t minus 4.9t squared. And even though t appears twice, it's the same variable, so I have one equation, one unknown. I can solve the second equation using some algebra by factoring out a t and setting one t equal to 0 and then solving for the other. And I get t is equal to 3.5 seconds and x is equal to 110 meters once I put 3.5 seconds back in. The third type of problem is mathematically a little bit more challenging, but in terms of what you need to do, really isn't. This is the combined problem. So now we have Thelma and Louise going off a jump off the cliff rather than just driving straight off. Now their 35 meter per second velocity, just like the General Lee, has a vertical and a horizontal component to it. So we have to solve, since it's still 35 meters per second and still 30 degrees, the way we get Vx and Vy is the same. So it's still 30.3 meters per second and 17.5 meters per second. The range, the x, is still what we don't know. The height is 100 meters or a negative 100 meter displacement. So plugging what I know gives me x equals 30.3t. Again, I can't solve this first equation because I have two unknowns. In the second equation, my displacement is negative 100 meters, again, because I'm moving down, equals 17.5t, so that's my vertical component of the velocity times t, minus 4.9t squared. Solving this requires using the quadratic formula. So the negative b plus or minus the square root of b squared minus 4ac divided by 2a, or just going to wolframalpha.com and saying solve and then typing the equation, which is what I did. So you solve for t. When you do that, you get t is about 6.6 seconds. You put the 6 seconds back into the first equation, and you get, this time it has a range of 200 meters. All right, so those are the three types of problems. We'll be working through an example of each type in class. But again, if you can identify them and you understand how each one of these three problems work, you'll be able to do the different types of problems in class also. Sometimes we're not always solving for range, sometimes we're solving for heights and other things. But again, you always go back to just these same two formulas here, and you work with them. You plug in all the things you know, and then use whichever equation only has one unknown in it to solve for it, and then plug into the other equation to get what you need. Okay, so hopefully this has been helpful for you, and we'll see you in class to work out some problems.